This is AP Calculus AB, and in this video I'm going to talk about section 5.5, which is linearization, and there's also some information in here about Newton's method that I'll present to you, but it's not really something that you're going to need to know, so we're going to focus on this idea of linearization. So before we get into linearization, we really have to talk about what a differential is. So differential expressions we've been seeing since we started doing derivatives. Whenever you see dy dx, that is a differential expression. And so a differential expression is essentially a variable, but it just has a meaning in terms of what does it actually mean when I say dx or dy. So when I say dx, I'm talking about a small change in my x value. When I say dy, I'm talking about a small change in my y value. Now, there's a couple of things about this that'll make a little bit more sense once we've done linearization. But the first thing is dx and delta x are essentially interchangeable. When I'm talking about how much I'm changing in the x direction, the dx and the delta x are the same. When I talk about dy and delta y are not exactly the same thing, and I'll explain why a little bit later on. But the main thing is the dy is my approximated change in my y value. Okay, so when I see something like dy dx, like you see here, that's essentially telling me my change in y with respect to a change in the x. So that's the same thing as the derivative, and that's one of the interchangeable derivative representations that we've used. So keep in mind, like I said, dy and delta y are not typically going to be the exact same thing. Okay, so when we talk about differentials, the big thing that I want you to get out of this for now is that differential expressions are essentially variables. So we can manipulate them in the same way that we can manipulate variables. So for example here, what we have is, you can see where it says dy is equal to f prime of x dx. Well, think about if I can manipulate these differential expressions in the same way that I can manipulate variables. If I divide each side of this equation by dx, I would get dy dx is equal to f prime of x as essentially the equation. So that is exactly what we've been using for the last month or two as we've been talking about derivatives. So keep that in mind. What that's also telling me is that an approximated change in the y value is equal to my derivative times the change in the x. And that'll make a little bit more sense here in just a second when we start talking about differentials. So the first thing I want to do here is just show you how you can rearrange these equations to solve for the differentials or just manipulate equations. So this is actually a differential equation. And we have dy is equal to 3x plus 7 to the fifth times dx. So a differential equation is just an equation with differentials in it. So since there's a differential dy, there's a differential dx, this is a differential equation. If they wanted us to solve for y, what we could do here is, and we'll see this in the second semester, we could actually integrate on both sides of this, but we'll get there later on. The other thing we could do is we could look at this and say dy dx is equal to 3x plus 7 to the fifth. And now we understand that's the derivative of my original function, and we could think about using an antiderivative, which I mentioned a little bit in the last video. We could use an antiderivative to figure out what y would be. And again, that's something we're going to get to down the road. For now, just understand that these differential expressions, we can move them around just like we can any other variable. We can add them, subtract them, multiply them, divide them, exact same idea. Okay, so that's really what these next questions are about. It says find the equation for the differential dy. When you see these types of questions, they're very, very simple. They're just trying to reinforce the idea that we can work with those differential expressions just like any other variable. So if I have y as 7x cubed, that means that dy dx is equal to 21x squared, and that means my dy is equal to 21x squared times dx. Now, what that expression tells me, and this is really what they're asking you to find, what that expression tells me is that my approximated change in y is equal to 21x squared times my change in the x. So that's what we're really trying to get out of that. Okay, so here's another example of that. We've got y is equal to cosine 4x. So if I found my derivative dy dx, Derivative of cosine's negative sine, so I'm going to get negative 4 sine 4x when I do the chain rule there. And then we just multiply the dx over. So my approximated change in my y value is negative 4 times the sine of 4x times my change in my x value. Okay, and then here's another one. We have y is equal to x cubed plus 2 to the 8th power. Same thing again. Take the derivative. I'm going to have to use the chain rule again here. 8 times x cubed plus 2 to the 7th times 3x squared. And then that would mean that dy is equivalent to 24x squared times x cubed plus 2 to the 7th power times dx. And again, my approximated change in my y is 24x squared times x cubed plus 2 to the 7th times my change in the x. Okay, so now we're going to get into this idea of linearization and what I'm talking about when I'm saying the approximated change in y. It's going to make a little bit more sense. So linearization, I often refer to as a tangent line approximation because that's really what it is we're taking the tangent line to a function at a point and we're using it to approximate the function for values that are close to our point of tangency. So this whole idea is relatively simple, but what I want you to realize is this is part of a much, much bigger idea in calculus, and it's the idea of something we call a Taylor series. And a Taylor series is a method that we use to approximate more complex functions by using really simple polynomial functions, and then we can do things like derivatives and integrals of a simplified function instead of working with a really complicated function. So we're going to see the most basic form of that. And if you take, let's say, Calculus 2 in college next year, or if you take BC Calculus next year, you'll see how this simple idea can be expanded into a much more complex idea of the Taylor series, which then will allow us to work with more complicated functions and get better results. So the linearization of a function, like I said, is essentially a tangent line approximation. Now, if you notice, it looks like we have a formula here, and we do, but this is not really a formula that you need to remember, because what we're looking at here is if I had the point a, f of a, let's say that was my point on my function, and I knew my slope was equal to the derivative at the point a. Well, if I plugged into the point slope formula, I would have y minus f of a, y minus y1 is equal to my slope, f prime of a, times x minus a. Okay, so that's the equation of the tangent line, right? Well, all they did to get what I have circled here, to get the linearization of a function, is they added the f of a over to the other side. So all it is the tangent line rearranged. So don't feel like you have to remember a formula for this. Just realize that we're just using the tangent line. Okay, so in the end here, what we're saying is if we want to approximate our function, we can use that tangent line to approximate our function for x values that are close to the point of tangency. And another way we can write this right here, f of a plus f prime of a times dx. So you can see this expression right here is how much I've changed in the x direction. That's my dx value. Okay, so let's take a look at actually how we use this. So if we want to do a tangent line approximation, it's actually a really, really simple process. Because we're just using the equation of a tangent line, there's two things that we need to know. The first thing is we have to know the function value at our point of tangency, and we have to know the exact value of the slope. So if we know the point and the slope, obviously that's how we get the equation of the tangent line, and that's what we're going to use to create our linearization function. So here's a really simple example that's been worked out for you so you can understand how it works. What we're trying to do here is we're trying to use a linearization to approximate 15 minus x cubed. So we're going to use the point of tangency to be the point on my function 2, 7. So the first thing we did here, here's my point, here's my slope, and here's the slope at the point when x is equal to 2. So I've got my point, I've got my slope, and then I can get the equation of the tangent line. Here's the equation of the tangent line. And then from there, all we're going to do is rearrange that. And now what we're saying is our function value can be approximated by negative 12 times x minus 2 plus 7 when we're close to the point where x is equal to 2. Okay, so that's really the end result of this, just trying to approximate a function by using a line instead of using a more complicated function. So for example here, if I were going to look at, let's say, f of 2.1. Well, f of 2.1, I could definitely plug that into the calculator and I could figure out exactly what it is, but what we're trying to do is just approximate. So the nice thing about this is I don't have to do 2.1 cubed anymore because I can just do negative 12 times 2.1 minus 2 plus 7. And all I'm doing there is I'm using that as my approximation. So in the end, I'm saying f of 2.1 is going to be approximately 5.8. And if you found f of 2.1 on the calculator, you would see that that's actually a pretty close approximation. And the reason that we're pretty close is because we didn't go very far from our point of tangency. Our point of tangency was at 2. We went 1/10 of a unit away. So I would expect that my tangent line would still be a pretty good approximation for my function. And in this case, it is very, very close. Now, where you have to be careful with these things is if you do an approximation and you're too far from your point of tangency. Like, let's say, for example, I were going to look at f of 7, and I'm going to approximate that. If we approximated f of 7 with our tangent line approximation, we would get approximately negative 53. Well, the problem with that is the actual value for f of 7 is negative 328. So we've gone so far from our point of tangency that our model is no longer giving us an accurate representation of what this function is doing. So now on that one, I'm just going to cross it out because in that case, I've gone too far from my point of tangency and my model is no longer accurate. So I would have to have a new tangent line approximation if I wanted to approximate f of 7. Okay, so when we think of the tangent line approximations, that stuff we did at the beginning with differentials, it's essentially what we're looking at there. So we saw in the formula how the differential expression showed up. So here is my tangent line, right? And when I move the 7 over there, I have essentially my change in y on the left side, and I have negative 12 times dx on the right side, but then I would add the 7 to the other side, and that would give me my approximated y value. But notice the y minus 7 that I have right here, that's my approximated change in the y is equal to negative 12 times the change in the x. Okay, so that's all we're really doing when we look at that dy is we're using the line to approximate the function. And I just want to show you that on this graph over here, just so everybody has a clear view of what we're doing. So we take our tangent line, and you can see the function here is actually concave up. But if I go out here some delta x unit away or some delta x distance away, my tangent line is not very far from the function. So that tangent line is still doing a pretty good job at approximating the function value. So that's what we're trying to do with those linearizations is instead of dealing with that more complicated function that's concave up there, we just deal with the linear function, which is very simple, and then I can approximate my function value. Okay, so one of the things we have to be careful with is the idea that if I were to look at the graph of a function, when I zoom in on that function enough, if it's differentiable, that means that eventually, if I'm close enough to that point of tangency, my function is going to start to resemble a straight line. And so that's what this is talking about. You can go through this on your calculator. You can plot that function. And if you zoom in on the point at x is equal to 0, even though at the beginning it'll look like you have a cusp in that graph or a corner in that graph, if you zoom in enough, you'll start to see that that graph is actually differentiable there. And you'll start to see how that graph starts to resemble a straight line very, very close to x is equal to 0. Okay, so that's essentially what I was talking about on this graph over here, that idea of local linearization. When I'm very, very close, and I know this got a little bit pixelated here, but I'm very close to this point of tangency, you can see very close, both of those just look like a straight line. So that's the idea that we're using when we do these linearizations, is that if I'm close to the point of tangency and it's a differentiable function, then the function starts to resemble a straight line. All right, so let's go through a couple more examples here so you can see the types of problems that you're going to be doing as you go through the assignment, and then we'll talk just briefly about Newton's method. So this question says, find the square root of 1.01 without a calculator. Now, you might ask yourself, why would I ever do that? I can plug square root of 1.01 into the calculator. Well, the point is we're trying to use something that is easy to quantify to do a linear approximation with, so we have an easy comparison that's easy for you to understand. So notice they didn't give us a function here that we're trying to approximate. So we have to come up with a function that we're going to use. And what I'm going to do here is I'm going to say f of x is the square root of 1 plus x. And if that's the case, remember I need to know my point of tangency, and I need to know the slope at that point. Well, if I plug 0 into that, I get exactly 1. And the reason that I chose my function to be the square root of 1 plus x is because 1.01 is very, very close to 1. So I knew that if I took the square root of 1, I could get an exact value. So that's where that came from. Now, if I get my derivative here, I'm going to get 1 over 2 times the square root of 1 plus x. And if I evaluate that derivative at 0, I'm going to get a slope of 1/2. Okay, so now if I want to do my linearization, remember it's just the equation of the tangent line. Y minus 1 is equal to my slope times x minus 0. And the last part of this then, I just move the 1 over to the other side. So y is equal to 1 plus 1/2 times x minus 0. And for our linearization then, what we're saying is that the square root of 1 plus x can be approximated by 1 plus 1/2 times x minus 0. Now, notice that I'm not distributing the 1/2 through there and getting rid of the 0. The reason I'm doing that is because I want to keep record of where that point of tangency was, because that tells me, okay, x equals 0 was the point of tangency. This approximation will work close to 0. Once I start multiplying everything out, I start to lose the representation of where that point of tangency was, and I no longer know where my model is going to work the best. So this point at x is equal to 0 is oftentimes referred to as the center point of our model. So I want to keep reference to that center point. Okay, so the last thing here is they want us to approximate the square root of 1.01. Well, that's going to be approximately 1 plus 1/2. And I'm going to need to plug in 0.01 for x, or 1 over 100. So that's 1 over 100 minus 0. So essentially 1 plus 1 over 200, and that would be 1.005. Now, if we do the square root of 1.01 on the calculator, you'll see that you get a value very, very close to 1.005. And if you do that on your calculator, what you're going to end up with is 1.49998. So you get a number that's very, very, very close. And the reason that it's actually 1.004987562. So the reason that I'm so close to the actual value is because we only went 100th of a unit away from our point of tangency. So I would expect my line to be doing a really good job of approximating my function when I'm that close to the point of tangency. Okay, so there's another one here, square root of 405. And I want you to pause the video, and I want you to use that one above as a model. And you can try to find the square root of 405 without using a calculator. So use a tangent line approximation and try to figure out what that value is. When you unpause the video, I'll show you the solution. Okay, so I may have done this problem slightly differently than you did, but this time I said f of x was the square root of x. And I did this in a little bit different way just because I wanted you to see there was more than one way to do it. But if you did it with f of x is square root of 400 plus x, you're going to get the same answer. It's just going to change how you calculate your delta x. or your dx. Okay, so with mine, f of x was square root of x. And then what I did is I said, okay, I know what f of 400 is. It's exactly 20. I found my derivative. Derivative at 400 is 1 over 40. So this value and this value are the key to the whole thing. And now I get my tangent line, and then it's just rearranging the tangent line. Sometimes you'll see the linearization function represented by L of x. So that's the linearization function. It's 20 plus 1/40th times x minus 400. And then from there, you can see that my change in x here is actually 5 units. So we get 20 and 1/8, or about 20.125. Now, if we were to do square root of 405 on the calculator, it's actually 20.1246118. So we got a value very, very close to the actual value. And again, it's because yes, we went 5 units away from the point of tangency, but at the same time, if you think about what a square root graph looks like, when I'm way out there on the square root graph, it's very close to linear. So I would expect that I could go pretty far from my point of tangency if my graph is close to linear. So that's what we were looking at with that question. So not really too difficult to do. If you had used the square root of 400 plus x, what you'll notice here is this value that you got over here, you would have had your center point to be at 0, and then you would have done 5 minus 0, and you would have gotten a change here of 5 units still. So you still get the same dx, even though you did a different function, and you'll get the same result because you got the same dx. Okay, so I've got one more of these that I just wanted to show you. This is what a lot of the problems in the assignment look like. So on this one, they give you the center point. It says approximate the cosine of 1.75 starting with x is equal to pi over 2. So there's not really anything different here other than the fact that they already gave us the function. In this case, I know f of x is equal to the cosine of x. I know f of pi over 2 because that's our center point. Well, cosine of pi over 2 is equal to 0. I know my derivative in this case is negative sine of x. And my derivative at pi over 2 would just be negative 1. Now for my linearization, get the equation of the tangent line. Y minus 0 is equal to negative 1 times x minus pi over 2. And then from that, I know my linearization function is going to be negative 1 times x minus pi over 2. And then I would do plus 0, obviously, but there's nothing there, so I just wrote it like that. And that means the cosine of 1.75 can be approximated by negative 1 times 1.75 minus pi over 2. Or you could write that as pi over 2 minus 1.75. And we could also get a decimal approximation for that. But that's the idea behind it. It's still the same thing we were doing. It's just that now the function's already given. So pretty simple to do. All right, so the last thing I want to show you here in terms of linearization is this idea of the difference between the differential value and the delta value. So what we're looking at is just a kind of a really basic application question. The radius r of a circle increases from 10 to 10.1 meters. Use dA to estimate the increase in the circle's area A. Compare this estimate with the true change delta A and find the approximation error. Okay, so I know my area of a circle is pi r squared. Okay, so if I took the derivative of that, dA dr would be 2 pi r. And I also know when I solve for dA, dA is 2 pi r dr. So what that expression tells me is that my approximated change in the area is 2 pi times the radius times the change in the radius. So now it said use dA to estimate delta A, the actual change. So dA is just my approximated change in the area. It's 2 pi. My original radius was 10. My change in the radius was 0.1 meters. And if I multiply that out, this is telling me that my approximated change in the area is 2 pi meters squared. Now, we want to compare that. What's the actual change in the area? Well, remember the area of a circle is pi r squared, so I'm going to do the actual change in my area. If I have the larger circle, pi r squared would be pi times 10.1 squared minus pi times 10 squared. So what I'm doing is just taking, okay, if I had a circle with a radius of 10.1, what's the area? What's the area of a circle with a radius of 10? And then what's the difference? How much did that change? Well, that changes by 2.01 pi meters squared. So you can see that 0.01 pi is the difference between my approximation and the actual change. So my error is just the difference between the two of those. So this is called an approximation error. And all we're going to do is find the difference between the delta value and the differential value. So delta A minus dA is all I'm going to do. And I put the absolute value there because you can put them in either order. We're just trying to figure out how far did we move in either direction. So in this case, 0.01 pi meters squared. Okay, so like I said, dA is the approximated change where delta A is the actual change. And that was really the main idea behind everything that we're doing here. I've got this graph here. It's not in terms of dA and delta A, but it's still the same idea. You can see that we've got this delta F here. So this is like, let's say this is my area function here because it's quadratic. So if I found the actual change in my values going along the area function, that would be like my delta A. And if I use the linear approximation going along the tangent line, this is the change from here to here. And that would be my dA. So you can see here they're saying delta L is equal to f prime of A dx. So that's my approximated change. Delta F is the actual change. But my dA and my delta A, that's what I'm actually looking at here. The difference between using the tangent line approximation, which is what using those differentials does, and using the actual change by using the original function. Okay, so you have a bunch of these kind of problems in your homework. The one thing I want to point out is with the error calculations, if you look in the book, you'll see a lot of different error calculations. The only one I'm going to ask you to know how to do is this approximation error, this example that I just showed you. So don't feel like you have to know all those different error calculations. That sort of goes beyond what the focus for us is. We're trying to focus on the calculus and not all these error calculations that we can do. All right, the last thing in here, there is some stuff in here on Newton's method that I put in the notes, not because you need to know it, but because it's a really simple application of linear approximations. And I put it in here for you to read through on your own if you would like to. So if you are somebody who is going to continue in calculus after this class, if you're going to be a math major, if you're going to go into engineering or physics, this is something that you're going to need to know how it works. You will go through this. If you take Calculus 2 or BC Calculus, you'll go through this in a lot of detail. But it's interesting to see it in the context of what we just did. Newton's method just uses a linear approximation to approximate the zeros or the roots of a function. So you can read through that on your own, and you can see how that works.